Day 15 of 75, and today we kill a bug that's cost more interview offers than any algorithm mistake. Reaching for STD, set by default. Your logic is correct, your complexity looks fine, and your solution still TLEs. By the end of these 5 minutes, you'll know exactly which of 3 containers to pick, and why the obvious one is usually wrong. Here's the classic trap. Two-sum variant. Find all values in array A that also appear in array B. Students make 3 wrong moves. Move 1. Dump everything into STD. Set 4. Fast lookup. Move 2. Nest a loop and call .count inside it. Move 3. Assume O log n means fast. The asymptotics are right. The wall clock is a disaster. Let's see why. Segment 1. STD. Set internals. STD. Set is a balanced red-black tree. Every insert allocates a separate node on the heap, each holding a value, a color bit, and 3 pointers. Lookups are O, log n, but every step chases a pointer to a node that could be anywhere in memory. That's a cache miss per level. At 10 to the power of 5 elements, you're paying main memory latency log n times per query. Bonus gotcha. Iterators stay valid across inserts and erases, which is convenient, but costs you that pointer-chasing node layout. Segment 2. STD. Unordered _ set. This is a hash table, so lookups are O, 1. Average. Genuinely faster than the tree for pure membership. But watch the constants. Buckets are linked lists, so each element is still a heap-allocated node. As load factor crosses 1, it rehashes and relinks everything. And the worst case is O, in a bad hash or adversarial keys collide every element into one bucket. In competitive judges, that's a real attack. If your keys are custom types, you're writing a custom hash, and a weak one silently turns O, 1 into O, n. Segment 3. The hidden third option nobody teaches, a sorted STD, vector with binary search. Same data, one contiguous block. No per node allocation, no pointers, no allocator overhead. Sort once in O, n log n, then STD. Lower _ bound gives you O, log n, lookups that march through cache lines instead of scattering across the heap. Same asymptotic complexity as STD. Set, but 3 to 5 times faster wall clock on dense integer keys. For that 2-array intersection problem at 10 to the power of 6 ints, the sorted vector wins on both time and peak memory. The tree wasn't wrong, it was just slow. Segment 4. STL set algorithms. Once your data is sorted, the standard library hands you the operations directly. STD. Set _ intersection, STD. Set _ union, and STD. Set _ difference. You give them 2 sorted ranges and an output iterator. Set _ intersection, A.begin, A.end, B.begin, B.end, back _ inserter, result. The gotcha that burns people. The precondition is sorted ranges, not STD. Set containers. The word set in the name means the mathematical set, not the class. Feed these an unsorted vector and you get silent garbage. No crash, just wrong answers. And prefer reserving your output vector over back _ inserter into a fresh STD set, because that just rebuilds a tree you didn't need. So when does each actually win? STD. Unordered _ set when you need pure membership checks, keys hash well, and order doesn't matter. STD. Set when you need elements kept sorted and you're interleaving inserts with ordered traversal. Sorted vector when the data is mostly static. You build once and query many, and you care about cache behavior or memory, which, at 10⁻5 plus elements, is almost always. Need set algebra? Sort, then call set _ intersection. Never handroll it. Decision flowchart. Start with the key type, then the size, then the access pattern. Custom keys with heavy lookups. Unordered _ set with a real hash. Need sorted order live? STD. Set. Build once, query many on dense data. Sorted vector plus lower _ bound, every time. Day 15 done. The takeaway. Container choice is a cache locality decision wearing a complexity costume. Subscribe for day 16, where we tackle multi-set, and frequency maps.